So good morning everybody. So today's class I'll be talking about the decoders. Okay. So let me tell you something about the decoders. The digital information whatever we have 0 and 1, that is the digital information represented in some binary form must be converted into some alternate binary form, and that alternate binary form is implemented by these decoders. Okay, how can we achieve this alternate binary form? We can achieve this by having a multiple input multiple output logic network, and that is known as decoders. Decoders have multiple inputs and multiple outputs. Always you remember this. Decoders represent the binary information in some alternate form, in some other way. Okay, the binary information is represented in some other alternate binary form, and decoders are multiple inputs and multiple outputs. Okay, and the most commonly used decoders are nothing but n input to 2 raised to n line output decoder. Okay, now this decoder, okay, so here in this decoder we have many types, like we have many types of decoders. N to 2 raised to n line decoder is a very commonly used decoder. Okay, so here n to 2 raised to n decoder is having n inputs and 2 raised to n outputs. Okay, it is having n inputs and 2 raised to n output lines. And this property, see, decoder is having one property. What is that property? It is having a property that one of the output line responds and says with the logic 1. Response means what? It is having one of the output line is having a logic 1 to the particular given input combination. Now for example, if the decoder is n is to 2 raised to n means what? N is number of inputs, 2 raised to n is the number of outputs. Okay, so always remember there are various types of decoders. Okay, so in that various types of decoders, the commonly used decoder is n to 2 raised to n decoder. So n inputs with 2 raised to n outputs. Okay, so here basically we are having n inputs and 2 raised to n output with the property that one of the outputs responds with the logic 1 to a particular input combination. I would like to say, like, if suppose we have 3 inputs at the decoders, okay, 2 raised to n, 2 raised to 3, that is 8 output lines will be having. N is to 2 raised to n means if n is 3, okay, n is the number of inputs, 2 raised to n is the number of outputs. Okay, so here n number of inputs is 3 means the number of outputs is 2 raised to n, that is 8. That is 2 raised to 3 means how many? 8. Now if suppose at the input side if I choose 0 0 0, okay, at the output side first output line will be selected. If I choose 0 1 0, then second, that is 0 1 second, third output line will be selected. Okay, so this is about the decoders. As I told already, it is the commonly used decoder is n to 2 raised to n line decoder. Only one of the 2 raised to n output line responds with a logic 1 to a given input to a given input combination of values on its n input lines. I told you n inputs lines will be there and 2 raised to n output lines will be there. Okay. See, this is the logic diagram, this is the symbol, and these are the truth table. This is the truth table. Let me explain you properly now. See students, these 3 inputs are there. Okay, x0, x1, x2, or you can also assert like x2, x1, x0. Okay, and how many outputs are there? 3 inputs means 8 outputs, because 2 raised to n is 2 raised to 3, that is 8 outputs. naming from 0 to 7. 8 outputs will be there. Suppose if 0, 1, 0 is selected, means this one will be, this output line will respond with 1. If suppose x2 is 1, x1 is 1, x0 is 1, that time the Z7 output line will be selected. Okay. So what is the functionality of this is, decoder represents the binary form into some other alternate binary form. That is 0 0 0 means first line, that is Z0 will be having output 1. Okay. Now similarly 0 0 1 means Z1 output line will be having 1, others all output lines will be having logic 0. Now what is this? It's an active high decoder. What is this? It's an active high decoder because its output is 1. So it is active high. Okay, output is 1, so it is active high. If output is 0, all others are 1, means it's a active low decoder. Okay, so this here you need to implement these outputs here according to this. So x2 bar, x1 bar, x0 bar will be given to this z0. Okay, next x2 bar, x1 bar, x0 will be generating m1. Okay, x2 bar, x0 bar, x0 will be given to this. So this will be generating z1. So according to these min terms, this one is realized. It is very simple, students. 3 inputs, 8 outputs. Okay. So what is for this to implement, what you want? You want 3 input AND gate. So these are all 3 input AND gates. Okay. And we are generating the output Z0 to Z7 as a function of 3 inputs X2, X1, X0. If suppose if you are selecting Z0, that is if the selecting Z0 means at the input side you have 0 0 0, then Z0 you will select, 0 0 1, then Z1 you will select, 0 1 0, then Z2 you will select. This one similarly you will try to draw with the, these min terms will be implemented with the help of a NOT gates and with the help of 3 input AND gates. So these outputs are generated by using with the help of these AND gates and these using these NOT gates. Okay. Truth table also says that. See, if the input x2 is 0, x1 is 0 and x0 is 0, z0 is selected. If it is 0 0 1, z1 is selected. All others are zeros. 0 1 0, z2 is selected. All others are 0. Similarly 0 1 1, Z3 is selected, all others are 0. Similarly, up till 1 1 1, we have Z1. We have selected this Z7. Z7. For 1 1 1, we have selected Z7. Output line as 1. All others are 0. So students, this is the symbol 3:8 decoder symbol with 3 inputs x2, x1, x0 and with 8 outputs z0 to z7. These min terms are generated with this help of these AND gate and NOT gate and the z0 to z7 output are realized. Okay. Next, these inputs and these are the outputs. Depending on the selecting of the particular input combination, particular output will be selected at one time and all others are 0.
Excuse me, ma'am.
Yes.
Ma'am, the input is only 0, 1 and 2, no, ma'am.
No. This is decimal number, Baba. 0, 1, 2. 3 inputs are there. Here you have to apply the inputs 0, 0, 0, 0, 0, 1 like that.
Okay, ma'am. Then it will be only till 2, no, ma'am. 0, 1, 0. Only 3 variables we will get from binary.
No, Baba. See here 0, 0, 0, 0, 0, 1, 0, 1, 0. You will get 8 combinations, no, here like this. 0, 0, 0, 0, 0, 1, up till 1, 1, 1, 8 combinations you will get.
Okay, ma'am. If the input is 3, then we should write 2 to the power of 3 variables
No.
in
If
the.
the input is 3 means 0, 1, 1 you should write. And 0, 1, 1, 3 means only at that time this Z3 will be 1. Z3 output line will be 1. All others will be 0. You understood?
No, I'm not getting that.
Not getting means
No.
at one particular iga 000, it is function specific decoders with less than 2 raised to n output exist. Example, decoder with 4 inputs and 10 outputs, in which a single responding output line corresponds to a combination of the 8421 code. What I am trying to tell here is n to 2 raised to n line decoder are commonly used decoders, okay, and there are other types of decoders also which does not follow n to 2 raised to n line decoders, okay. There may be variable inputs and 4 inputs 10 outputs like that, okay. And the 7 segment output decoder also accepts 4 bits of the 8421 code and is used to drive a 7 segment display. It need not be n to 2 raised to n line decoder only always. There are some other types of specific decoders also, okay, like for 8421 code generating and next for 7 segment display, okay. Next, moving on to the next one, logic design using decoders. Like logic design using decoders means we are trying to have a min-term generator. Like I have specified here, an n to 2 raised to n line decoder is nothing but a min-term generator. By using OR gates in conjunctive with an n to 2 raised to n line decoder, realization of Boolean functions are possible. Okay, they do not correspond to minimal's SOP. Decoders are nothing but a min-term generator. They are not minimal sum of products generate. They do not generate minimal sum of products. They only generate min-term. And they are simple to produce, particularly convenient when several functions of the same variable have to be realized. Okay. So here n to 2 raised to n line decoder is a min-term generator. Okay. It does not generate minimal SOP. Okay. So now here min-term generator using OR gates. Min-terms that can be generated using OR gates, that is x2, x1, x0. There are 3 inputs and 8 outputs. Okay. So here 3 inputs are there. 3 inputs are there, that is x2, x1, x0, x2, x1, x0, okay. And here see 2 functions are given, that is f1 of x2, x1, x0, that is summation m 1, 2, 4, 5. f2 is given, that is 1, 5, 7. So here using the OR gate we can just realize the Boolean expressions 1, 2, 4, 5. So 1, 2, 4 and 5. We have given it to a OR gate. Next 1, 5, 7. 1, 5 and 7. We have given it this to another OR gate which realizes function f2. Okay. So here these are 0, 1, 2, 3, 4, 5, 6, 7. These are the output lines. 0, 1, 2, that 2 corresponds to x2, 1 corresponds to x1, 0 corresponds to x0. These are the 3 input lines. These are the 8 output lines. Okay. Now we are realizing the functions using these decoders along with the help of this OR gates. Okay. So summation m 1, 2, 4, 5. We are just pulling up the wires 1, 2, 4, 5 and then giving as an input to this OR gate which realizes function f1, because these generate min-terms. What does these generate? Min-term. And what are these 1, 2, 4, 5? These are min-terms. The summation m means you should have a OR gate. Okay. So 1, 5, 7. Similarly 1, 5 and 7. These generating min-terms. Summation m means you should use a OR gate which realizes function f2. Okay. Now next one. So this is again x2, x1, x0. These are the 3 inputs and these are the 8 outputs. Okay. So realize the Boolean expression. So see, this is a OR gate. Summation m means OR gate. Summation m bar means not of OR, that is NOR gate. Okay. Summation m means OR gate. Summation m bar means whichever the terms are not present here, that will be present in the summation m bar. See here, f1 of x2, x1, x0, summation m 0, 1, 3, 4, 5, 6. So what is not present in this? That is 2 and 7. So it is 2 and 7 are not present. So it's a complement of this. So complement means you have to take a bar upon it. So summation m 2, 7 upon the bar. Next f2, x2, x1, x0, summation m 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 6. What is not present here? 0 is not present, 5 is not present, 7 is not present, right? So summation m bar. So not of or. It is not of or. So that will be NOR gate. Okay. So 2, 7. Pull the lines 2 and 7. Put a NOR gate. Next. Pull a line here 0, 5, 7. 0, 5, 7. Okay, so you will have this functions to be realized. Okay, so now here f1 and f2 are realized using the help of the NOR gates. Okay, so your summation m means OR gate, summation m bar means not of OR, that is NOR gate. Okay, so next we have implementing a decoder using NAND gates. Okay, so here using NAND gate means we have not of and, not of and. So now for example, how many outputs? Same type it is, n inputs, 2 raised to n outputs. x2, x1, x0 are the inputs and z0, z1, z2, z3, z4, z5, z6 are the outputs. Okay, so this is a NAND gate. Okay, not of AND. So that is, so we have x2 bar, x1 bar, x0 bar, then complement this, you will get a max term, right? So implementing a decoder using NAND gate is a max term generator. It is a max term generator. So similarly x2 plus x1 plus x0 is m0. Similarly z1 we have x2 bar, x1 bar, x0 full entire bar, that is x2 plus x1 plus x0 bar, that is capital M1, that is max term generate. It is generating a max term M1. Similarly up till we have M7. Okay, so this is the logic diagram for the decoder, implementing a decoder using NAND gate. So this here again we have 3 inputs, 8 outputs. NAND gate, so we have a bubble here which generates a maxed. Okay, these are the inputs, these are the output. As it is a max term using NAND gate, okay, 0, 0, 0 means max term means it is high when it is 0. Even in K-maps you group zeros, no, for max terms. Similarly like that it is active low decoder. So only bubble is there. Okay, it is a active low decoder. For a particular combination x2, x1, x0 is a 0, 0, 0. When you apply a input 0, 0, 0, z0 output line is selected. All others are not selected. Similarly 0, 0, 1, z1 is selected. All others are not selected. Okay, since it is an active low decoder, so it is a 0 here in this diagonal. You can see it's a active when it is low. It is low means it is a logic 0. Okay, it's an active low decoder, and this using this NOT gates and NAND gates we generate the max term, and hence it is known as a max term generator. It is a max term generator. Okay, we cannot realize minimal expressions from decoders, but we can implement the min terms and max terms using the decoders. Okay. Next, we have max terms using these AND gates also we can generate. Okay. So here summation M we have actually 0, 2, 6, 7. Okay. And next we have 3, 5, 6, 7. How do we generate this? Now 0, okay, 2, and here we have, okay. So similarly this summation M can be generated by using this NAND gates. Okay. So here we have 0, 2, 6 and 7, and we have there F1, okay, and we have here F2. So can you see students this one how we are implemented it? It is a active low. It's active low. So we can also realize the SOP using this active low decoder. Okay. So any doubts in this slide?
Where is 6 and 7 connected?
Where?
6 and 7.
See, it is summation M. It is summation M, no? Yes or no?
Yes, ma'am.
That means these are min terms. What these are? Summation M means what? Min terms, no? But here we are, what we are doing here? What is this? It generates max terms. Yes or no? So here what is not there? 0 is not there. 1 is not there. 2 is not there. Okay? And 4 is not there. That only we have to write as F2. Because see here, this decoder actually implements max term. But we are trying to implement min term. Isn't it? Max term and min term are complement of each other. So here what is not there? Here 1 is not there, 3 is not there, 4 is not there, and 5 is not there. So that we are going to implement using AND gates. Okay? Because these generate max term. But this is a min term here. Min term. What terms are not there here, that will be implemented by this decoder. Okay, that is 0, 2, 6, 7 we have, 0, 2, 6, 7 we have. What terms are not there here? 1 is not there, 3 is not there, 4 is not there, and 5 is not there. Similarly, 1, 3, 4, 5. Implement using AND gate. Because these max terms are complement of min terms, isn't it? So complement means how to write a complement of this. Write a complement of this means what you will do? Whatever the terms are not there, no, that you will write. Okay. So what terms are not there, that you have to take and put it in a AND gate. Because max terms are complement of min terms. And here which terms are not there? 0, 1, 2 and 4. So similarly 0, 1, 2 and 4. So implement it using AND gates. Okay. So this is a max term generator, but we are trying to implement summation M, that is min term. So because this is a max term generator, we need to take the complement of this. Complement means how to take it, by whichever terms are not there, that we have to take and then pull a line and implement it using AND gates. Okay. So next we have decoders with an enable input. So we have an additional input E. If E is 0, this will not be active. Okay. If E is 1, then only it is decoder is active. Fine. So we have here 2 is to 4 means 2 inputs means 2 raised to 2, that is 4 outputs. So x1 x0 are the inputs. Okay. So if it is 0 0, no, 0 0 with the enable 1. Enable should be always 1 in order to one output should, if you want to select one output, enable should be high. Okay. And here we have two inputs x1 x0. If it is 0 0, z0 is selected. Okay. If it is 0 1, z1 is selected. If it is 1 0, z2 is selected. If it is 1 1, z3 is selected. Students, what are these x1 x0? These are the inputs. These are the inputs. Okay. You have to switch these inputs, apply the various inputs and get the particular output. I repeat once again, apply various inputs to this x1 x0 and get the particular output. If it is 0 0, z0 is selected. That is the same thing, it is explained in this compressed truth table. If enable is 0, irrespective of the x1 and x0, no output is selected. Okay, if E is 1, then only it will be activated, because we have here E. It is an additional input which activates this decoder. Okay, so when 0 0 Z0 is selected, 0 1 Z1 is selected, 1 0 Z2 is selected, 1 1 Z3 will be selected. I repeat once again, enable is an additional input which activates this decoder. If enable is 0, this will not act as a decoder. In order to act as a decoder, enable should be always high, that is 1. Enable should be 1, then it acts as a decoder. So any doubts in this slide? So next, decoders with the enable inputs. Okay, when disabled, all outputs of the decoder can either be at logic 0 or logic 1. Enable input provides the decoder with the additional flexibility, that is, data is applied to the enable input. Sometimes the enable input line can also be used as a data line. Okay, this process is known as demultiplexing. Okay, so what happens here, students? If this is 0 0, no, this enable will act as a data line. Whatever the data is present at the output, that will be seen at the output Z0. Okay, if it is 0 1, whatever is present here, it will be present at the Z1. If it is 1 0, whatever the data is there here, that will be present at Z2. If it is 1 1, whatever the data is present at the enable, that will be present at the Z3. It is, enable inputs are very useful when constructing larger decoders from smaller decoders. Okay, so this is about this decoders with the enable inputs. Okay, so next we have constructing larger decoders with smaller decoders. So here we are constructing here 4:16 decoder using 2:4 decoders. So here 2 inputs, and here also we have 2 inputs. Okay, so 2 inputs, x3 x2 is applied to the first level of the decoder. Okay, and here we are applying this one. So here we have the construction of this 4:16 decoder. Like here we have 16 outputs. Okay, and we have 4 inputs here. Like x3 x2 is applied to the first level of the decoder, x1 x0 is applied to the second level of the decoder. Okay, so here when I select this x3 x2 as 0 0, no, this line will be activated. 0 1 here, this line will be activated, that means this decoder will be selected. 1 0, second line will be activated. Here 2, second means this 1 0 line will be activated, this decoder will be selected. And 1 1, the last line will be selected, so this will be enabled, so this decoder will be selected. So whenever we have 0 0 on this line, 0th decoder will be selected. This is the first decoder will be selected, because this term is given as an enable to this. Okay, if it is enabled, then this will be selected. So first 4 min terms, first decoder will be selected, that is 0 1 2 3. In the next 0 1, second decoder will be selected, that is generating min terms 3 4. Okay, so 3 4 5 6 7. Next 1 0 means the third decoder will be selected, 8 9 10 11. Next 1 1 means we'll be selecting this. Okay, it is the last decoder having 12 13 14 15 combinations. Okay, so here we have here this one. So we have constructed the larger decoder using smaller decoders. Okay, so any doubts in this? Some PPT, I think it can't. Any doubts in this?